The Bike Club podcast is a collaboration between Beth Karan and Akshaya Parthasarathy.
The Bike Club podcast acknowledges the traditional custodians of the land we record on. We pay our respects to elders past, present, and emerging.
Welcome to Bike Club, a tech podcast crafted by the girls for the girls. Our mission to elevate, educate, and explore the exciting world of technology.
So tune in and remember, the first rule of Bike Club is to talk about Bike Club. Hello everyone, and welcome to episode 5 of Bike Club. This is so exciting. We're halfway to double digits. This week we're going to be talking about another amazing woman in science. But first, I'm going to get Akshaya to tell us the rule.
Oh, yes. Thank you, Beth. Rule number 4 for this episode is to embrace the embarrassment.
Yes.
So if you've got a thought that's keeping you up at night and it might just be replaying some embarrassing moment that has happened that day or even just the previous week, I say we embrace it and eventually just let go of the embarrassment. I don't know about you, but oftentimes when I've kind of either acted out of character or just been a tad bit more confident than what I usually am, that moment tends to replay in my head until it reaches a point of agony. So
torturing yourself with it,
pretty much, yeah. So I'm trying to tell myself that instead of telling myself, why did I do that? Why did I say that? Let's try to picture the role model that we have in our head, or rather the most confident person that we know of, and think, what would that person have done in that situation? And I think that helps you get over it much better. And it also helps you realize that as much as you're overthinking or getting embarrassed by it, the people who did witness you at that time probably don't have any thoughts to say on it. So just let it go.
They've probably already forgotten, to be honest.
Yeah, exactly.
Like, the things that we dwell on, people probably are not paying attention to.
Exactly, yeah. So, yeah, don't sweat the small stuff and just remember to embrace the embarrassment.
I love that. I have 2 things to say about that rule.
Yeah.
First thing is I follow this girl on Instagram and she talks about this concept of cringe mountain. In order, like, all successful people, all people who've like done cool things with their lives have had to climb cringe mountain to get there. Like, you have to embrace the cringe of like being new at something.
I love that
and
term. Yeah, cringe
not really
mountain.
knowing what you're
Wow.
doing and like putting yourself out there and being a bit uncomfortable. You have to get through that to like get to the place where you want to be. Otherwise you just stay in like complacency.
Yeah.
And I love that language of like, everyone cool has climbed cringe mountain. It's an important part of growth. You can do it. Like, we're all doing it together. So yes, embrace cringe mountain. I think is great. The other thing is, we were just talking about this, Kashaya. So just before we started recording, we were talking about how obviously we've kind of talked about our podcast at our shared workplace a little bit, like, and it's kind of like, it's a bit scary to be like, this is this thing we're doing. And one of our co-workers came in and he was he like came into the office and he was like, welcome to Bad Club.
Yeah.
And he kept like
cringy,
teasing us about it.
Yeah.
Yeah. And we were like, it was out of love. Like, he's actually listening and like, we hope that he hears this. But we were like, stop it. It's so embarrassing.
Part of the process.
We're embracing cringe mountain. We're embracing the embarrassment.
Yep, we're climbing cringe mountain. I love that.
Yep. All right. Brilliant.
All right. Take us away, Beth.
Thank you. I think that's a great rule. So today I'm going to be talking about Radia Perlman and spanning tree protocol. Are you familiar with this?
Yes, actually. She was one of the ladies that came up in, while doing the research for one of the episodes. But I'd love to hear this more because I've not looked at it in detail.
To be like, as a disclaimer, networking is kind of the field of computing that she works in, and it's also one of the fields that I'm like the least knowledgeable or experienced about. But I wanted to pick someone who worked kind of in something that was outside of my I guess, training in my field because I wanted to learn about some new stuff. But if I like get anything wrong or like I say something dumb about like networking, feel free to either Akshaya like correct me or send
Oh,
me an email or DM me on Instagram and be like, that's not what that is. Like that's totally fine because I'm learning along with all of our listeners.
yes.
So yeah, I'm figuring out as I go. So that's my disclaimer. I'm not a networking expert, but hopefully I can give a decent explanation
I'm
of
sure
what she
you'll
did
do
because
great.
it's pretty
Yeah.
cool. Thank you. So Radia Perlman, born in 1951,
Mm-hmm.
and grew up in the 50s and 60s in New Jersey in America. I actually related a lot to a lot of aspects of her story because in school, she was like, liked maths, liked science, like those kind of fields, but she was never the kind of person who would like take things apart and try and figure out how they work. Like we talked about last time with Hedy Lamarr, that she was
Yeah,
always
I was
that
just
kind of
gonna say the
very,
opposite of Hedy Lamarr.
yeah, exactly. Like, which is often the kind of stereotype that you get of like innovators or inventors that like they were born wanting to tinker with things, but she
Yes.
said she was never like, that concerned with it. She just liked maths and thought it was cool. But she was the kind of person who was like, oh, if I take it apart, I'm probably going to break it. Like,
Oh, yeah.
which I was the same.
Hard
Yeah.
relate,
Yeah.
honestly. Yeah.
So I found that very encouraging. But she said while she was at high school, so it would have been in like the 60s, late 60s, a school teacher saw that she was quite adept at maths and science,
Mm-hmm.
and suggested that she go to a like out of school computer science kind of learning program that a
Okay.
local university was running. So they like were trying to get people, because this was the early days of computer science and computing as an industry, and so they were trying to get young people who were interested in maths like into the computing field. And so they were like, send your top math students over and we'll do like computing boot camp kind of thing. So she went to that. She was like, sure, whatever, that sounds fun. And she felt really out of place. So I have a few quotes from here, which is from an article that Netgear did, which I'll link in the description
Okay.
of this episode. That's a really great article because it's actually an interview with her. So she talks about all this different stuff. She's still alive. She's, I think, like 73 now.
Oh,
So
okay.
she's still, actually 2 years ago, she did a Reddit AMA. Um, and so there's like all this long thread of her like answering people's questions. I'll link that as well. It's so fun to read because
Oh,
she's like
how
such
cool.
a,
Yeah.
yeah, she's like such a great personality, and she's just like talking to all these like random people who are
Better
like,
people,
hi.
yeah.
Yeah, it really fun to read if you're interested in that. But this is one of the quotes that she gave to that article that I was talking about,
Mm-hmm.
around the camp, or not camp, but like program that she went to. So she says, everyone was bragging about how they built ham radios when they were 7. I had no idea what a ham radio was. And then they were asking questions with fancy words like input. I had no idea what they meant, and so my mind shut down. I got nothing out of that class because I felt I was so many years behind I'd never catch up. If someone
Oh.
had asked me what I was interested in doing, I would have said anything as long as it's reasonably interesting and doesn't involve computers.
Well, that's gonna be not possible with the degree that she chose.
Well, yeah, I'll get to that. But she said, when I learned to program a few years later, I realized it was fun and not difficult. But the experience made me understand the sense of panic that can cause someone perfectly capable of learning something to fail because they believe they cannot do it.
Oh my
Um,
God. Yes, it's so true because just
yeah.
sometimes you're so intimidated because of the concept that before you even want to dive into it, you're already saying, I can't do this. Like, this is not
Yeah.
my cup of tea.
And that I found that really resonated with me because I like when I was in kind of primary school, like younger, I
Yeah.
very much was like convinced that I wasn't good at maths, that I like couldn't do maths or science just because I like found it intimidating, and I was like more of an English kid, and so I was like, oh no, like I'm just I'm like not good enough, like I'm not smart enough, I can't
Yeah.
do that stuff. And it wasn't until high school that I had some really good teachers who encouraged me that I actually was like, oh, actually I can do maths and I can do sciencey stuff. And then, I've ended up going into a technical field. So I really related to that in terms of like it's super easy to feel scared off of things when people are kind of throwing around jargon or being like,
Mhm. Making
I've
it
been
very
doing
less
this since I
accessible
was
for
6
you.
months old.
Yeah.
Yeah, it's like, but I haven't been
Yeah.
doing that, so I'm not good enough.
Oh, that's fair. Yeah. I did think that science and math were right up my alley, but the moment
Mm,
I joined my engineering undergrad and when I saw there were people beside me who were probably coding since before they could even walk, I thought, nope,
yeah,
this is
yeah.
not for me. But yeah, I mean,
Yeah,
swear,
it's
yeah.
a very, very relatable thing, I think, for women, but for everyone, honestly. Like, I tutored a lot of people when I was in, like, later in high school, and so
Yeah.
many people I tutored in maths were like, I'm just not a maths person, I just can't do it. Like, it really is, anyone can learn it, and it's not something to be scared of. But anyway,
Yeah.
to get back on topic, after that kind of off-putting experience, she decided to just study pure maths at MIT at uni when she went into her undergrad. So she wasn't interested really in doing computing at that stage. She did maths, she did a few physics subjects as well. And another quote from her talking about being one of the very few women in the program. She said, "I'd noticed that it kind of looked weird when this other gender person looked curiously out of place in the crowd. I'd have to remind myself that I was also the other gender." So there was so few women in her courses that when she saw another woman in a class, she was like, "What are they doing here?" And then she's like, "Oh, wait, I'm
that's
here."
the patriarchy.
Yeah, it's that like internalized, spend so much time around guys. It's like you forget that you're not, just in a sea of men. Like you're like, oh yeah, wait, I am actually different. I thought that was a funny quote. And then, so while she was doing that, she obviously did quite well at uni. Did pretty well in her physics subjects that she was taking, and one of her professors for a physics subject needed like an intern to do some programming work at a company that he was working at. So he was doing like teaching and working, and he was working at BBN Technologies, who at the time were kind of a very groundbreaking technology company, who were developing some of the earliest networking like technologies. So this teacher was like, "Hey, I see that you have this natural ability for like problem solving and maths. Would you want to come and do some programming for me?"
Oh.
And she was like, "I'm not a programmer. I haven't, like, that's not my training." And he was like, "I know, that's why I'm not paying you." So he basically was like, "I can justify getting you to work for free since you're not qualified."
Yeah. Okay.
Which is like, isn't that
best? Not the best way
it's
to get work, but okay.
Yeah, it's so classic, like university being like, "I'll just pull this person; they can probably do it, and then if I get them to do it, I don't have to pay them." So
yeah,
it's like you get paid an experience, exactly.
Yeah.
So she did that, and she quickly discovered that she actually was really interested in computing and specifically network engineering. And so she, after doing that for a little while, the unpaid role, she took a paid role at BBN Technologies, and she really got into kind of the technical side of things at that point. So a little bit of background on BBN, who were the company she worked for. They were the developers of the ARPANET. So it's like kind of one of the predecessors to the internet.
Yeah.
So ARPANET, it was kind of like, prior to this, they had Ethernet networks. So you could connect like, 2, 3, 4, a few computers onto a physical wire, and you could send information that way. But ARPANET was the first kind of like dial-up network. So the first one to use telephone lines and connect computers across large distances and across, a whole organization or like a whole university, or have these kind of larger scale networks. And lots of educational and like corporate settings were beginning to use ARPANET. And so that was kind of their flagship product, and that was kind of starting to be used more broadly when Radia joined the organization. So one of her first papers that she published, so this was like the early 1980s at this point, one of the first papers was identifying a crucial flaw in the ARPANET network. Since all of the computers are connected, and so there's lots of different ways to get from any one computer to another, messages could get stuck in like loops or duplicate infinitely. So if it was a message, say, that was sent out to be like, "Please send this to all these computers," and then all of those other computers have systems that say, "Well, if it comes to me, I need to send it to this other computer," you could end up in these like infinite loops. And so messages would just go back and forth forever, and then you would, like, the whole network would crash and you'd have to restart everything. So she identified this need for what she called self-stabilization. And you do still want to have multiple ways to get from one computer to another, because if one route goes down, then you still need to get information between them, right? So that's called redundancies. You want to have redundancies in your network so that if one path is blocked, you can still get stuff between computers. You still need to have that as an option, but you also need to not have loops. So how do you have a bunch of different computers that are all connected to each other, where there's multiple paths from each one to each one, but you don't have any loops in the system? Like where something can go from one computer to the second computer to the third computer back to the first computer.
Yeah, that's an interesting problem. Without the issue of duplicacy as well, because you don't want like the same thing appearing twice.
Yes, exactly. And cluttering the network, which is then eventually what causes it to crash, because think you've only sent one thing, but effectively you've sent 20 things because it's just bouncing around the loops in the network. Her manager at BBN challenged her to find a solution for this. So on a random Friday, this manager comes up to her and says, this is from the article, Radia, we need to design a magic box that sits between two Ethernets and lets somebody on this one talk to somebody on that one. Something she'd been designing kind of for years. She'd been trying to make this work. And he also said, you have to make it so that there are no rules on how you plug it together. You could have a bunch of drunk monkeys with Tinker toys and it would still work with zero configuration.
Okay, so it's basically if it works kind of a situation.
Yes, it needs to work on its own. So
right, yeah.
And this is kind of where it's different from like way back in the day, you know how you have those old movies where they talk about the circuit switching, like the women who sit on phone lines and they like take the cable out of one port and they put it into another one. Yeah, exactly. So it's like, yes, you could technically wire up every possible combination of computers with their own individual wires, but that would require a lot of configuration and a lot of mapping for any sort of computer network that you wanted to use. And so the idea was that this needs to be something that just works on its own. You can't have people having to configure every possible path.
Yeah, an autonomous network, basically. Yeah.
Yes, exactly. Yeah. So a bunch of drunk monkeys should be able to operate it.
Right.
So this was on a Friday, and then the manager was actually on holiday the next week. So he gave this problem to Radia, being like, good luck, probably won't have any progress by the time I get back, but here's something to chew on while I'm gone, kind of thing. Like, here's something that will keep you occupied until I'm back.
Okay.
But actually, Radia had a bit of a brainwave, and she figured out the solution almost immediately.
Oh, yeah, go Radia.
I know, it's amazing. So she had it working, like she had an idea of it that weekend, and she had it completely written up and like fleshed out by the next Tuesday, which is just amazing. So she said, it was such a simple algorithm that I wrote the spec and it was complete by the end of the day on Tuesday. It was so complete that the implementers got it working within just a few weeks without even asking me a single question. But this was the Tuesday and my manager wasn't around and I had to show up and I couldn't concentrate on anything else. So the remainder of the week, I worked on a poem that goes along with the algorithm. It's so excellent. So this is one of the probably the only networking solution that comes with its own poem.
Oh my God. Okay.
Yeah. So
nice.
I'll read you the poem now. It's pretty short, but it's so great. She included this on the paper that she then published of how this works. So the poem goes, I think that I shall never see a graph more lovely than a tree whose crucial property is loop-free connectivity, a tree that must be sure to span so packets can reach every LAN. First, the route must be selected by ID. It is elected. Least cost paths from route are traced. In the tree, these paths are placed. A mesh is made by folks like me, then bridges find a spanning tree.
This is how I want to learn every single
I know, it's so
concept
excellent.
From now on. Yeah. Not only did she check the challenge, she just went that extra mile and did her little haha. Look what I
she's like, I've got 3 days. I'm going to just write a poem. So as you might have guessed from the poem, the solution, and from the beginning, the solution is called the Spanning Tree Protocol.
Right.
It works incredibly well, and it was slowly adopted by computing companies all over the world over the next couple of years. She also went on to write multiple sort of foundational textbooks in the field of networking, and she's been recognized in things like the Internet Hall of Fame and the Inventors Hall of Fame. So yeah, this was a super significant invention, and she really came up with it in a couple of days, which is just amazing.
Wow. Yeah.
One thing that she talks about a lot in some of the interviews that I watched with her is this idea of, monkeys should be able to use it, like this very intuitive design. And I think a lot of that comes from her experiences way back when she was a kid of feeling kind of blocked out of technology stuff because she didn't know all the jargon. And so when she's designing things, she wants it to be very intuitive and she wants it to be very user friendly. And I think that's what actually helped her come up with this solution, because instead of looking for the most complex way to do it, she thought, well, what's the most simple and clean way that I can do it? And then she built up from there, which I think is, really, really inspirational, because it can be easy to get bogged down in kind of all the technical details and being like, well, I have to incorporate this and this and this. But she actually just went, what's the most logical, simple way that I can possibly solve this problem?
Wow. that is very insightful.
So that's a bit about her and a little bit about Spanning Protocol. I'll get into how it works in our next section. But yeah, that's Radia Perlman's story.
Oh, very well summarized, Beth. Thanks for that.
No worries. Alrighty, so we've heard about Radia's story and how she got into tech, and now I'm going to talk a little bit about how the spanning tree protocol works. So
Mm-hmm.
again, if I miss things or I say something dumb, I apologize. Feel free to let me know. But this is my kind of best explanation of how this works. So as we talked about earlier, one of the issues that it was trying to address is this idea that you could end up with loops of information going around and around.
Yeah.
So the simplest way to imagine it is just to imagine 3 computers. Say if you have like a triangle of computers and something's going from computer A to computer B, but it actually just sends it out to everything on the network because it's trying to get it, it's trying to make sure that no matter what happens, it gets to its destination. But because it's now sent it out to computer B and C, C is going to go, oh, this is for computer B, and it's going to send it across. And so then you get those duplicates, right? So B has received it twice.
Yeah.
Which is okay in a small system because B can just look at the ID of the communication that's been sent and say, okay, well, I already received this, so I can just delete it.
Right.
But when you have like hundreds and hundreds of computers, you end up with heaps of network congestion, potentially even to the point that it can crash the entire network.
Of course, yeah.
Yeah, so that's one of the issues. And then the other thing that this needed to solve is that, as I was saying before, you could just have a dedicated line between each and every pair of computers, right? Like you could have one computer has a distinct connection to every other computer in the network. But
Okay.
that is so many connections.
Yeah.
Like
and that's a lot of network load on just that one computer, which
yes, exactly.
it's
that
not
computer
very
has to be talking to every other computer. It's super like cost inefficient because it uses so much power. Like it's just not a good idea. So those are kind of the main issues that they were trying to address. So it's the, reducing the loops and also the scalability, bringing the scalability. So you can have 10 computers on a network or you can have 1,000 computers on a network and it'll work either way. The way that spanning tree protocol works is it's kind of like you can imagine it as like a traffic control system.
Right. Okay.
So if you imagine like a city, and you have a bunch of like houses or buildings that you want people to be able to get between. You could just have a bunch of roads with no kind of traffic controls and everyone could just free for all and find whatever path they want to find to the place. They'd probably get there eventually, but you might have like accidents so people are coming in from 2 sides of a road. You might have people who get lost. You might have people like it's just not the most efficient way for people to get from one place to another just by going to each intersection and guessing like, okay, well, I guess I'll go this way and then that'll get me closer. And, you have people going, multiple directions on the same side of the road. Like it could be a disaster. So instead of having that, you have things like traffic lights, which tell you, the people who are going along this direction, this intersection can go and everyone else has to wait. And even more so, you might have everyone in the car has like a GPS. And so the GPS can look ahead, it can look at the path that you're trying to go down, and it can map the shortest possible path. So instead of just going around any random path that you decide, the GPS will tell you this is the shortest path to get to the place you're going. It might even tell you if there's like a blocked, if there's an accident on the road, and it'll say, avoid this path and go around. And so then you can make sure that you don't end up in a pile up or, you don't end up in an accident or stuck forever. The ways that you can sort of model this is you can imagine traffic lights like switches.
Right,
so you can imagine them like switches on the network where it tells the signal which computer or which path it should go down. And then you can imagine there's sort of like, imagine if there's like a highway and there's sort of branching off of that. That's something that we call the root bridge.
Right. So it basically represents a tree.
Yes. So it's a spanning tree. And that's where the kind of brainwave came for Radia was instead of looking at this as just a series of interconnected dots, what if we modeled it as a tree and we kind of selected a route, and then as everything travels along, its purpose is to get back to that route and then find the best path from the route to the destination. So everything kind of comes back to the root bridge is what it's called. And then it travels back out to where it's meant to go. And the algorithms that it's using, so the algorithms that it's using are to calculate the most efficient path from the route to any given destination.
Okay. Oh, sorry to cut you off, but I think and I didn't want it to make it sound so trivial, but I feel like the representation of Radia's algorithm is in that animated movie Wreck-It Ralph.
Oh, yeah.
Yeah, it's actually in the second part. There's quite literally like a police officer that sits in the center, and he sends it across from like the different branches. Oh my God.
Yeah,
Wow.
exactly. Yes. I totally forgotten about that, but that's a great image of it. So yes, the algorithm is the one that basically says which way to go.
Yeah, yeah.
And so if you model it this way, you still have multiple interconnected paths that something can take, right? So like if one of the paths goes down,
Mm-hmm.
then you still have that redundancy where you can reroute to a different
To a
path
different one, yes.
that is the next most efficient, but you don't
Yeah.
have all of those paths kind of functioning at once. So you only have one most efficient path between any two computers operating at any time,
Okay.
if that makes sense. So it's kind of
Okay.
like path selection based on this tree. And the way this is done is that there's a signal sent out from where you are wanting to send something. So there's a thing called a bridge protocol data unit, which is basically like a little test message that goes out from the sender and
Mm-hmm.
it queries the path. And so it looks for the best path and it finds if there's any loops in the path. It finds if there's anywhere that you could get back to your current computer through this tree. And if there is a loop, what it does is it tells the system to turn that loop off. It says, we don't need that path at the moment, that's redundant. So turn that on, off, and then it basically forces the message to go down the path that is most efficient.
Mm.
So instead of telling the message, make this turn and then make this turn and then make this turn, it's more like the GPS saying, this road is blocked, you have to go this way. Basically, the I can't say this, BPDU
Ooh.
is the little message that goes out and it queries the whole system and it goes, is there any loops? Is there any unnecessary paths that we don't need to use?
Mm.
And so close those off and then go down this path instead. So you want to keep those paths available in terms of you don't want to not have them at all, because
Mm-hmm.
then, as I was saying before, like if you get stuck somewhere or if there's an issue on the network, you want to be able to reroute into a different path. But for the purposes of this send, you want to have it closed off because you don't want the message to end up stuck in a loop or go through multiple paths and duplicate. You don't want it to happen. So that's where this little probe message comes out and it's like, what's the
Mm.
best path? What can I close off for now? And
Mm-hmm.
then say the network was to crash, it would then open back up those closed off paths and you could then
Mm.
go down that one to get there and it still wouldn't cause a loop because now the other side is blocked.
Yeah, that's a very fault-tolerant system.
Exactly. And that's the
Yeah.
whole idea. So one question I had when I was looking at this is like how do route bridges work? So if we have this route, which is like the main highway and everything spans off of that,
Mm-hmm.
but then there's like hundreds of computers in the network, like which one is the route? Like how do you know what the route path is?
Yeah.
Because you could have a tree spanning out from every single different computer, right? In theory. So this is where the idea of route bridge election comes in.
Okay.
And basically, it's a really simple solution. Again, Radia loved to do things that were intuitive and simple. All the devices will have an address. So they all have like a unique ID that says this is this device. It's a MAC
Mm-hmm.
address or
IP
a
address. Yeah.
bridge,
Yeah.
an IP address. Yeah, you can basically
Yeah.
think of it that way. And literally what this does is it just looks at the entire system and it finds the smallest value, like the lowest number in the system of the IP address, and it just picks that one.
Oh, okay.
So it's deceptively simple, and there is like logic behind how these IP addresses are assigned. Like more powerful computers will often have lower ones to kind of, utilize this system the best way possible.
Mm-hmm.
But because it's all just like it's a layer three, it's on top of the hardware. It's just a virtual thing that's happening. It kind of doesn't matter. And so basically, it just looks at the whole system and it says, what's the lowest IP? Pick that one, and that's the root. And so
Mm.
then the spanning tree network is set out from that place. That becomes the root, and anything on the network can navigate back to that root path and then out to wherever they're going.
Right. Okay, but
So,
the route path still changes dependent on the message that's sent.
so the root bridge stays the same, but then
Okay.
the path that it's taking is dependent on what loops are happening, what paths it can possibly take, where it should
Ah.
be blocking off a road versus where it should be opening up roads, which is what those little probing messages do.
Yeah.
But the route path is set. I believe it does changed. And again, this is showing my ignorance towards like networking
Network,
science.
yeah.
But I believe the root bridge can change. I would assume that's when you like restart a network or you add a new computer to a network.
Yeah, yeah.
It
No,
can
that makes
change.
sense. Yeah.
That's basically how it works. You have this root path, you have the spanning tree, and then messages can go back and forth along it. It stabilizes, it's called network topology stabilization. So many fancy words in this explanation, but it basically is the whole system it stabilizes the topology. So topology is just the study of paths. And so it stabilizes all of the possible paths where only the best paths are active and the inefficient or redundant paths are blocked.
I love the simplicity of the algorithm. I really think it boils down to how sometimes you don't need to complicate a concept just because it looks really intimidating. So it's just if it works, it works. And I love that she
Yeah.
made it work with something that was this simple. But I mean, it
Yeah,
still takes a
exactly.
lot of brain power to come up with something so simple. So.
Yeah, so for sure. It's like deceptively
Yeah.
simple in terms of like it is quite complex to implement.
Yeah. It shows how much of a great understanding she has on the concept, basically.
Yeah, for sure.
Yeah.
And I will say that I was reading about, in modern computing and even back then, like a certain computer could access the network and like force the root bridge to switch to their computer. So say a company, like an office, they're all on the same network and the most powerful computer in the office is owned by like the IT guy and he wants to make sure that the root bridge is on the most sturdy machine. And so what he'll do is he can go in and he can, by network engineering, he can communicate with the network and say, switch the root bridge to my computer, and then everything goes back to that. So you can kind of obviously fiddle with it, and that's a lot of what people learn when they're learning how to set up networks and learning how to connect
Very cool. Yeah.
various devices is those kind of commands where you either query the root bridge just to figure out where it is, or you'll set it yourself. And so you can do all that kind of stuff to optimize your system. But yeah, the part where the kind of it just picks based on the lowest ID number, that's where it's kind of, I guess monkey proof in terms of it doesn't matter how you set up the system.
Yeah.
How many computers you have, like it will find a path, it will send out the signals, and it will figure it out for you.
No, thanks, Beth. Yeah, I think you broke it down really well.
Okay, I'm glad.
Yeah.
I feel like I was kind of fumbling through that one because again, it's like not an area that I'm super familiar with.
I get it. It's a lot of alien concepts. It's a lot of new concepts. But I think the picturization with, the highways and all of that. It really did help.
Yeah, so I've got like the key concepts here and I might even like put these in the notes. But like, yeah, so you can imagine just your main intersection or your main highway is the root bridge. You've got traffic lights that allow you to have the active paths. You've got blocked off roads, which are the blocked paths. Yeah. And then you have like a GPS that can do the rerouting, which is the topology reconfiguration. So those are the main concepts.
Sounds good.
And that all works together to make it work, which is amazing.
Yeah, that is pretty cool. And if anyone's still a little bit more confused, they can just watch Wreck-It Ralph too.
Yes, exactly.
Yeah.
just watch that scene and you'll be all set. All right, so now we have a bit of an understanding of how spanning tree protocol works. I'll talk a little bit about, I guess, the developments that have happened since then and what the state of computer networking or network engineering is at the moment. So obviously since then we've had the internet, which is like the biggest implementation of this. And this is where spanning tree protocol and many other kind of protocols that have been built on top of that system are used not only over a wired system, but over a wireless international system where you have millions and billions of computers. I saw something that was like the estimated number of computers in the world is like 10 billion now, which is insane. Wow. But kind of makes sense when you think about it. Most people
all of them running on the basis of like the spanning tree algorithm. To some extent, of course. Yeah. Wow.
It's wild. Yeah. You then kind of have like trees within trees, if that makes sense. So like you'll have, your local network, which is all the people who are connected to your router. And then you'll have your area network, which is like your potentially your suburb
your MANs, your WANs and your LANs.
Yeah, exactly. Yeah. So you've got those kind of levels of network. And so depending on what you're accessing, the spanning tree will kind of go back to whatever level is appropriate. Like if you're just accessing something that's on your local network, it's not going to go all the way back to the root bridge of like like, that it would go to if you're going to be searching something on the internet. But because everything is like, almost everything is on the internet now, it's largely kind of at that top level. But yeah, I don't know if you were like, I know that I always had friends in high school who had like LAN parties where they would have like their
I've
local
heard of
network.
them,
They
but
would have
we've not
friends
had
over
it.
and like play video games in their local network because it was like way more efficient than trying to play online. I never did that because I wasn't a techie person or a gamer when I was in high school. But now I know what it
don't think
means.
I
I
did
was
that.
always like, what is a LAN party? I think I thought it was like land party, like LAND, like they're all in the same
No, it's just
land.
Just connected on the network. No.
Yeah. So that blew my mind when I figured that out. But yeah, so obviously the networks that we have now are way bigger, they're expansive. It also comes back to this the Internet of Things that we talked about last episode, where all of those individual devices have to kind of find their way back to the root bridge, either on the local network if you have like locally connected things like your smart fridge or your TV box or whatever devices you have.
Exactly. Yeah. They have to interact with each other on the same network. That makes sense.
Yes, exactly. But they won't like, you'll find that if you go to someone else's house, you won't be automatically connected to their smart TV or their whatever it is because it's on their network. And so you have to then tap into that local system. So that's largely one of the uses for it, apart from just like paving the way for the internet. And a lot of the places that I saw were referenced Radia as like the mother of the internet, because having that kind of scalable system is really what allows the internet to expand indefinitely. But I've also seen that she doesn't love that title. So I'm hesitant to like call her that, but some people do call her that.
Okay.
I think she finds it a little bit grandiose.
Cringe? Yeah, I was just gonna say that's her cringe mountain. So
she's like, yeah, exactly. It's her. Like, don't talk about me like
don't
that.
call me that. Yeah.
Nowadays we have things like quantum networking, which is crazy. Like people trying to use like quantum mechanics as like switches, instead of like a physical switch or a switch in a network. It's like a quantum switch, which I don't even like know how that works.
Yeah, I'm not sure too much about quantum computing either. That feels like a lot of leap for me to.
Yeah, it's really complex, but basically instead of an on-off, it gives you like on-off both. It gives you more options in terms of your switching conditions.
Right. Okay.
But obviously that's very much in the research stages. I don't think they've managed to get a quantum computer to work like at room temperature yet. So, but yeah, then you've also got like cloud networking. So you've got your which we use a lot in our workplace because we do a lot of data work over the cloud. And so that's where you have like a virtual network. So you'll have a virtual network that is all connected. They're all connected to each other, but they exist in like an isolated system so that you can have better security. You can have, no one who from outside that virtual network can access whatever's in the virtual network. And you can do development on a local network, which is much less, I guess, labor intensive for the broader network and also for the computer, because you're only talking to the computers that are hooked up to this virtual network.
Virtual network, exactly.
If that makes sense. So those are kind of some of the uses for it now. Obviously, again, networking is like a huge field, and it's how the internet runs. It's how we even have connectivity across the world. So it's hard to kind of summarize and be like, these are the couple of applications. But there's lots of exciting things happening, and there's lots of things that will probably just make it cheaper, like more scalable, faster as we kind of go forward. And who knows where we'll get to eventually, but
no, I love that. But I also think even if we are talking about the future, I think the biggest takeaway from this one is to just keep it simple. And who knows, you might just get like the next big breakthrough for
exactly. Even if you have what seems like an impossible problem, there might be a really intuitive and simple solution to it, right? Like,
well, thanks so much, Beth. And also thanks to everyone listening. I think Beth was mentioning she's going crazy over the analytics recently, and you noticed
hey, that's our
you
job.
love
so
graphs. Like, we get it. Yeah. We've been getting a lot of listeners in from, I don't know. Where was it, Beth? Sweden, was it?
Yeah, we've got some from Sweden. We've got Germany, New Zealand.
Oh, wow.
Mexico. It's very exciting.
Oh,
Japan.
my God, yeah, it's so exciting. We are, we're still so early with the podcast. So it's really nice that you're all tuning in and listening to us. So thank you so much for that. And in case you weren't already aware, we're on a lot of platforms right now. So you can basically listen to us across Spotify, YouTube, Apple, and everything where it distributes from Apple, Samsung, as well as Amazon Music and via Alexa. So if there are still couple more podcast apps. So in case you cannot listen to us wherever you are, just let us know and we'll make sure to make that happen.
Yeah. Honestly, if you can't like find the podcast at this point, then that seems like a you problem. Like not to be like mean, but also there's like a million options now.
You've got no excuse not to listen to us at this point. So
exactly. I was just going to say, we do have an exciting episode coming up next time. So definitely stay tuned for that. We actually have a guest coming in, which is super exciting.
Very cool.
We're hoping to do guest episodes every now and then, just to kind of get some perspective on other women who are currently working in the tech field, hearing about their experiences, just having a chat about life as women in tech, hearing about whatever cool technologies they're working on. So we're really excited for that. Stay tuned for that. You get to meet our guest, and it's someone who's very near and dear to my heart. So yes, very excited for you all to meet her. But
I'm also very excited about that. Yeah, it'll be good. So both you and I can take like the classroom seats, and we get to learn something new that way.
Yeah, we get to hear from someone different, which will be really exciting. So hopefully that'll be a great episode.
Awesome. Well, that's it from us. Thanks again for listening, everyone, and speak to you next time.
See you, everyone. Bye.